The broadcast is now starting. All attendees are in listen-only mode.
Yes, sir. Please go ahead.
Okay. What happened to the screen? Okay. If I make the screen bigger, okay, so good morning. I'm not sure if you can see the slides on this side, left-hand side,
Oh, yes, I can.
but how about the, so if I make it bigger, like the slideshow, it's going off my screen. Let's say resume slideshow. If I do that, I can't see the, I'm not sure if it's behind the scenes. I don't know.
Just put it back in the regular mode.
Okay, let me check. Pause. Play. So there is slideshow options on this side.
No, nothing.
So should I make it bigger?
Yes.
So let me try in the slideshow. You can see my mouse, right?
Yes. Yes.
Yeah, it's going off my screen if I do that.
Okay. You can just start presenting in the regular mode. I don't think we can solve that now.
Okay. Good morning, everybody. So I'm actually, can see my name, it's Raghu Echempati. I'm at Kettering University, that's in Flint, Michigan, USA. So today they gave me an opportunity to give a webinar under the IUCEE and try to give you some tips about including real life examples in your education. Most of what I'm going to show you or present or talk to you, you already know those. We already know those, but seldom we put them into practice, including myself. So we'll try to basically remind ourselves to put some of these into our practice in our lessons. So the webinar is going to help inspire instructors to use some of the examples, real life examples from literature, and also to develop more examples with the help of students. So this is going to be an exhaustive project if you really do it first time. So if you have a class of 40 or 50 students, you can really engage all the students in an active learning environment to discuss, brainstorm, and when you do the homework, you try to find an example, ask the students to find a real life example of those textbook problems. Now that's going to be very challenging for them. So you might have to help them with a few examples first and let them come with their own examples. And I would strongly suggest first time don't judge the quality of their examples. There could be anything. So let them do anything that they like. You can actually discuss, all this should be done in about 5 to 10 minutes because you still have a lot of syllabus to cover in your classes. So this should not be the main topic of your classes all the time. It will take a lot of time. So just be careful. So I'm going to present some examples from solid mechanics and a couple of examples from finite element analysis areas. But I also have examples in heat transfer, fluid mechanics, vibrations, thermal stresses, and so on. So I'll show you a web link that some of you can look at and perhaps use it. We discuss what you already might know about Bloom's taxonomy, and then we talk about 5 E's like engage, engineering, etc., and some introduction to active learning. So basically, if you look at what's engineering, there are different engineering fields. These are comics from Agilent technology. They are big supporters.
The slide is not moving, sir.
The slide is not moving?
No.
So there's a pause screen here. I don't know how to.
You should see a play button.
Yeah, I see the play button on the right hand side.
And does it have a drop down below it?
Okay, let me see. There's a drop down button.
And what are the options?
Show only screen. Is that the one that you're talking about?
Yes.
So screen, clean, hide, hide icons and background. We don't want that, right? Just a screen.
Yes.
Okay. I put the screen mode, and then if I, let me just do this. Okay. So now I lost my file. It's not here. Go back to screen sharing. Okay, so show. So is this better?
Yes, yes.
Okay. So I'm sorry about that. So there's some of the examples you can see. I sent a PDF file to your the webinar organizer. So those who are interested in some of the slides, you can get those, I think. So this one is called World Without Engineers. So I don't want to spend too much time. So basically this comic tells about aeronautical engineering. I think you can see that. The next slide talks about probably screen sharing is paused. Okay, so this one is like probably civil engineers. And then telecommunications. So without engineers, there will be problems, you know. So this could be like computer science, and so on, right? There are different areas in engineering. So the purpose of showing the comics is, are you still seeing the screen or no?
Yes, engineers are inventors.
Okay. So basically the purpose of showing those comics was that how can you make it fun? I never liked that word fun in engineering for many years. Even now I think engineering is not really, it's a serious business, but still how can you make the learning fun? That's what most students are nowadays. So young professors also like to include some fun. And so I think it's good to have some fun with engineering. They should also know the seriousness of engineering. Engineering also is serious. So we use the STEM education, including the math and sciences, and we got different branches of engineering. And this is a very important thing. As a student, I used to observe a lot of stuff around me, trains, buses, road signs. Then you got the equipment, sports equipment. So if you ask the students to observe many things around them, tables, chairs, everything, we know these things already, but we need to emphasize to students to look at some of the things around them and then bring those, how they relate. Those examples, like for instance, it's a chair. Now chairs, there are different kinds of chairs, different designs, and if they can tell the attributes of a chair, the load carrying capacity is not the only criteria, then of course they can always put maybe a stone, right, for a chair. But stone doesn't always look good, so there's some aesthetics, there's transportability, there's so many other issues besides just the engineering functional design. So I think we can discuss those quickly and make the students understand that functional design is just one thing, aesthetics, strength, materials, there's so many other aspects in engineering. We all know that engineering is perhaps only about 40% of a product life cycle. And the rest 60, majority is management, materials, and other marketability, and so on. So business perspective is now included in many of the engineering courses. So we need to do that. So engineering is only a little bit, half, less than half, but the rest is how to bring a product to the market. So in that context, if we can include some examples, the students will get excited. Okay. And again, there are different sub-branches within mechanical engineering, like automobile and power generation, space, agricultural equipment, and then the airplane propulsion, then mass production, air conditioning, HVAC, CAD, bioengineering, like codes and standards are very important. So we got courses in thermal fluids, heat transfer, energy systems, etc. Again, we are familiar with this. Okay, so as long as you see the screen, that's fine, but I have some issues showing up on my screen. I actually developed a course on design with aluminum.
Let me show the slides and you can just say next when you want me to change it.
Okay, why don't you do that, please? Yeah, that'll help me. So, can you see the slides?
Can you see them?
Oh, yeah, now it's better.
Is this the one you're on?
Yes.
Okay.
So you got CAD, you got bioengineering. Bioengineering is like 50 different areas. There are tissue engineerings, minimally invasive surgeries. We got blood, we got prosthetic devices, bones, and then of course animals, lab animals. There's so many things in bioengineering. It's not just biomedical devices. Bioengineering is a huge area because older people are living longer and they're also living healthy, old people. Old means age-wise. And then so they need the bones, etc. intact, but that comes to us only mainly through food and maybe meat and other products, proteins. So basically, the bioengineering is emerging area, as most of you know. Along with that, the CAE, the computer-aided engineering and technology, being able to do solid modeling of the three-dimensional surfaces, three-dimensional objects is getting very important. Now, codes and standards probably are not very strict for everyday products, for all the products in India, but I think it's coming up from when I visit India. There are a lot of emphasis now on safety standards, and there are not many codes and standards apart from automobiles, medical industry. Of course, there are some standards. codes and standards are there, but following those and how serious the government follows, people follow those is definitely very important. 5 codes are very important. Building codes, they're all very important. Can go to the next slide. So again, in the automotive area, we got lightweight, energy efficient, fuel efficient, etc. I think I can go to the next slide. Next slide. Okay, so the typical programs, if you look at, these are the standard programs. There is nothing much change in some of these areas, but the way we teach them is the one that we're trying to learn a little bit today, and we already know those. It's a question of being able to practice those. Okay, go to the next slide, please. So the next few slides basically tell typical courses. These are some of the courses that we teach. They may not be exactly at the same level. So at the broad base of the pyramid, you got math, science, fundamentals, English, language, and then the humanities, social sciences, and they also continue in the engineering core subjects, and then we're going to different specialized areas, mechanical, electrical, civil, and then we got within those technical electives, and then a capstone project. I think this is common for many universities. Under each one of those, on the next slides, you'll see some classes. So again, these are not, probably all of them may not be taught at your college, but most of those are common. Go to the next slide. In the core, if you go, basically go back to engineering core. One slide, yeah, okay. So you got mechanics, statics, dynamics, and then we got mechanics of solids, fluid mechanics, thermodynamics. So they're all hardcore prerequisites. And if you see the thermal fluid area stream, like fluid mechanics, heat transfer, thermodynamics is required, but only, I would say, from what I taught when I talked to other instructors, the percentage thermodynamics prerequisites is probably only of the order of 20 to 30%. That means if somebody skips thermodynamics course, can they take fluid mechanics? The answer is probably yes, and definitely it's useful to have thermodynamics. The purpose of thermodynamics is to build their thought process in their mind, so they can use the thought process, entropy, enthalpy, and all that cycles into other classes. But if you look at the mechanics stream, vector calculus, you got statics, the free body diagrams that are required in many other classes like strength of materials, dynamics. Then you get into vibrations, you get into finite element analysis, machine design. So there's a strong background required in statics and strength of materials. That's why people try to emphasize thermodynamics, statics, and solid mechanics courses, because they will be backbone courses for the other advanced courses. Okay. And go to the next slide. Then there are some other ME core courses. Again, they might not be exactly in the same order in your college, but to go to the next level, to the next slide. Then you got specialized electives in specialties. At Kettering, like many other colleges, we have some specialties: biomechanics, we have mechanics, manufacturing, and we don't have nuclear. I just showed those on the slide because some of you might have those. Aeronautics could be part of mechanical, but some have dedicated departments in aeronautics, obviously. And so again, this is by no means the only example of technical electives. We got many. So usually technical electives consist of 3 to 4 courses, 3 to 5 classes maximum. Okay, go to the next one. Then again, we got capstone classes, which are based on each technical elective. Somebody is in biomechanics or biomedical or biomechanical, then they have different capstone projects with more emphasis towards biomedical applications. And normally, if you look at the last line here, the real world design projects are attempted in the last semester. So that's the one we are trying to push down. That's the goal of this webinar. And most of us try to do those. For instance, if you can we use the real world examples in solid mechanics? Can we use real world examples in dynamics? The answer is yes. We already know that. If you look at the textbooks, at the end of the textbook, many examples are real world examples. But some of them, the students might not have seen those, but many of those, they understand, they see it. We got the power from, we got YouTube available now. We can probably play short video clips to diversify the monotonous teaching in a classroom by engaging students to watch YouTube and then engage them into discussions and then come with their own examples. So we can put that in active learning atmosphere, and that's what we strive to do. Sometimes we forget, sometimes we don't have time, and but the students actually like those. I think we know that. Okay, go to the next slide, please. Again, I'll go through quickly because it's actually, we do all these things, different types of motion, linear motion, reciprocation, rotary, oscillating, and there are examples. Now, some of these examples, like if you look at the IC engine, nowadays many students actually look at the piston cylinder engines. So you have in your college maybe a cut view of a real piston cylinder mechanism that you can borrow and show them. Because many students have not seen a piston, and they saw the pictures, they saw the photographs on internet, but they haven't touched and felt those. Particularly when you discuss the tolerances, the fit and tolerances between piston and cylinder, and they don't understand. They don't have a feel for it. So to create a feel, I call it a touch and a feel. If they touch, then they can feel it. So if it is possible, I show them a lot of components. I have many of those in my office, and I basically carry those and then show them to touch and feel. I don't know if it is 60 students in a classroom. Sometimes it's difficult because they get diverted. Each student will engage in discussions. When they touch the piston, it might take some class time because you are now lecturing and they are engaged themselves in talking about the piston. So it looks like, so probably have to give them a pause. We don't do it in a big class, but it is some classes to basically make them interested in listening to us, and then importance of it. Ferris wheels in amusement parks, they might have seen it, might not have seen it. You can show video tubes, and then I'll show you some things that we can discuss. It's not just mechanics, but we're going to talk about safety for the Ferris wheels, and then the societal impact. So those are the higher level in the Bloom's taxonomy, they call it. And again, you've heard those, and we just want to stress those. So we can go to the next slide. Again, these are not uncommon. We show these. We can show some small clips. We can show the real life examples from internet. But my emphasis is, have the students seen this, touched and felt it? So that's what I'm looking at. If we can try and let them feel by touching it, and that makes it interesting for them. Okay. Okay, go to the next slide. So if you go to the next slide, then you can see the wedge principle. So the principle of wedge or inclined plane is used in many applications like worm gears, screws. If you show them simultaneously, the helix angle, the thread angle, which is already there in machine design textbooks, but a real wedge, like in the red one, top left, that helps them understand what a wedge is. Like door stoppers, we put a wedge for stopping the door. If you show them really, and then compare that analogy between a wedge and then the friction with the worm gear, and then you show them, discuss how to reduce the friction. Just putting oil is not just one example. If you want to reduce the oil, because there will be some losses in a gearbox if you put too much oil. And the fuel economy, there are new designs in design of gearboxes where the oil is there. When oil gets thicker and thicker, more use, it becomes viscous. There are viscosity losses due to friction. It's going to cause more. So there are modern methods that they are doing research in automotive companies, how to reduce the friction, how to reduce the churning losses, because the liquid is going to agitate inside a gearbox. So I know some of you might be doing PhD or masters, but the question is, how do you get this idea into the undergraduate student's mind? So try to push it down. So that's the whole goal here. Okay, go to the next slide. So when we discuss the lever principle, there are many examples in which the lever principle is used. So I just am requesting, besides the three figures that we see on the top, the load to effort and the fulcrum, we know those from physics. But the real life examples and the safety of those designs, piano, excavator, weighing scale, when you weigh, it depends on what you're weighing. Obviously, if it is precious metal like gold, there's some importance in reducing friction, again, in a weighing scale. We can't design those as mechanical engineers, but just appreciate the effect of friction when you do weigh precious jewelry, etc. It's the same lever principle by showing real life examples and show them and then discuss. Okay, so go to the next slide. Again, wheel and axle. Again, you can show some real life examples of those, and I'm sure you do show those. We can't draw this on the board, it's very difficult. We must show examples. Okay, the next slide. Belt and pulley applications. Okay, go to the next slide. You can ask them to look at their elevator if they are living in multi-story buildings. Obviously, it's too dangerous to look inside the elevator, but just ask them, maybe by opening a door carefully when it is safe. Now the examples in gears is much easier because we do carry gears in the labs, so students get to see those. They probably make gears in your production labs. Okay, go to the next slide. Cams, go to the next slide. I do carry all these components in my office, so so I basically carry some of the leaf springs. I don't have all the leaves in a leaf spring, it's pretty heavy, but we do have a lab in which we can show those and then discuss the design. You know, the leaf springs, they're made of composites, one piece, with variable thickness and cross sections in a composite leaf spring. We can discuss those. That opens up new ideas in students. Again, at the solid mechanics level, machine design level, not at the senior level. At the senior level, they are already mature They may also lose interest because they're searching for jobs now. So there's not much innovative things that they're looking for because they don't have time. So we're trying to do all these simple examples at a lower academic level, like junior, second year, when they're taking solid mechanics, machine design, thermodynamics, fluid mechanics. So as many examples as possible. So I'll show some examples so you can see it's possible to do that. If we go on the next slide. So the Bloom taxonomy is the one that I want to spend some couple of minutes. We do show some of the applications, but if you look at the Bloom's taxonomy, there are a variety of figures they show, graphics. The lowest level is the one in which people just remember, and when we set the exam or the homework or discussions in a classroom, if we keep this Bloom's taxonomy as a play card in our hands and then focus the topic, homework, lecturing, discussions, exams, questions, etc. around this at each lecture for each class, that will help us in making the students very creative, which is the top one. So we should have some questions like facts, recall facts and basic concepts. Questions like define, duplicate, list some of the advantages of this versus that. Repeat, we state, ask them to define. So this they have to probably remember something, and that's at the lowest level. You can't have an exam only based on that. You can't have an exam based on create, on the top one. That's actually very tough during exam. But probably 90% of the time, we're at the middle level, like apply. Because in the next level, after remember, you got to understand, in which we can ask questions like explain the ideas or concepts of a certain thing. Explain the difference between, now it's not just the definition, now they're explaining a little bit more than just defining something. So classify, describe, discuss, so then now they have to write some communication. So there's some language that they have to go through to explain, to communicate their ideas in a discussion, like asking them back in a discussion or an exam or in our lecturing, we explain things. So that brings us to the second level. And then normally we also execute in the next level, solve, demonstrate, interpret the results, etc. So that takes us to the application level. And then we try to connect in the analysis stage, differentiate between this and this. And so these are different than the previous two levels. In the connection among the ideas. Use this idea to do something else. And that sounds very important. So you teach something and then ask something else, different field. And for example, if you take a shirt, a simple example, it's not a very good example, but if you take a shirt which is torn, then we use the shirt to cover the body, but now we can reuse it. One is to reuse it. One is to use a shirt, torn shirt, maybe to mop floors. We do that all the time, don't we? Or we can use the torn shirt to clean the car. Now, a shirt is not really used to clean a car, but we are trying to reuse in a different way for a different purpose. So we do that all the time. Things that are designed for a certain purpose are used in a different repurposing, different application. So that thinking, asking questions like that, will basically make them more draw connections among the ideas. So that's just a simple example. We do those. And in engineering, how can you reuse, for example, bearings? Bearings we use for machine components like systems, but when they're worn out, how do you use those? Bearing has to be used as a bearing, maybe for a, on an agricultural farm for bullock cart. or horse-drawn buggies, or for some other not critical applications. We do those. But the question is, we need to ask them, when the bearing is worn out, how can you repurpose and use it for a different purpose totally? So that's analysis stage. It requires a lot of practice on the part of the instructor to draw the connections among different ideas. But how do you get the students to think about it? So that's the goal. And then they evaluate. We actually do those. And in capstone classes, we try design, assemble, construct. That's the create. But question is, how do you bring that higher level in a lower level classes like solid mechanics? So that's the goal here. Okay, go to the next slide. So now if I give a practical example, compression members. So we have stress equal to load divided by area, and the deformation is PL divided by AE. For those who are familiar with solid mechanics. So the goal here is stress and deflection when a member is subject to different types of loading. So we've got axial loading, bending, torsion, combined loading, etc. And there are similar examples for thermodynamics, fluid mechanics. And in this case, the question is how to find the stress here. Now, if you give the load, if you give there are three variables here. One is the material, one is the load, one is geometry. So material is connected with the stress. So how much a member can sustain, how much stress. So that depends on the material, Young's modulus, etc. And then the load is connected to what kind of load is acting. It could be fluid load, could be mechanical load. There's nothing like a concentrated load in real life. Distributed loads, gravitational loads like self-weight, and so on. So that's a load. And then the geometry is a length area. Now, if we just give two numbers and then solve for the third one, that's at the lowest level. Okay, so most examples in old textbooks used to be give any two out of the three variables. The fourth variable could be a safety factor. So we introduce safety factor normally in machine design, but many of us now introduce safety factor also in solid mechanics. So that brings us to the fourth dependent variable, like a safety factor. So if you give any three of these four, then you find the third one, then the fourth one, that becomes a lower level. Becomes a little bit more complicated if you ask them to find the shape of a cross section, and so then of course that becomes a little bit tough because, for example, if you give a material, they know the yield point stress for it, they know the safety factor should be more than 1 if it is given. If you give the load, and then if ask them to find a certain shape, so that becomes beyond just the area. The area is just a number. If they find the area is 2 inches squared, for example, or 200 millimeters squared, there are many shapes I can come up with to satisfy that area number. So now, if you really do closed form solutions, will the stress be exactly the same for when the area of cross section shape is hollow tube, for example, thin hollow tube, solid circular tube, if it is square, triangle, hexagon, there are different shapes for the cross section that gets the same area number, but the stress won't be exactly the same, like what you calculate by formula. It just gives us the average, but not the maximum. Maximum will be different in each one of these cases. So that's what we can emphasize, and we know that the students can see that now. So so basically we play around with that. Now, also the next type, the next complexity is who gave this load to us. If we say 60 kilonewtons, now how did you get it? So rather than telling some numbers like 60 kilonewtons, if you can also ask them, where is this 60 kilonewtons coming from? What is it due to? Can you tell me an application of that? So that's going to be now challenging for them. That means they need to get a feel for the amount of load, the amount of pressure, the heat that we are talking about in classes, the source of that load, the source of that number, and then a feel and an application. So that becomes tough for them, for us also. So most textbooks, statics, basically tells us how to predict how much load is coming in on the members. So basically we discuss that. We know those, students perhaps know it, and we just want to discuss and ask them to come up with another example from practical applications aspect. Go to the next slide, shows some. So the trust example is common. In this example, they also find distress. But now we're not telling them, we're not giving the load directly. We just give them indirectly. We solve this already in our classes. So if you mix problems with real life applications after we teach the concept, put more examples like this, and that'll be interesting to them. Now the truss, they might not have seen it. This is just a 3 or 2 lines. We put forces, they do method of joints or sections, and then they find the forces. That is still at a lower level in so-called Bloom's taxonomy. If we can take them to the next level, which is on the next slide, which is an application of the truss. Now we can tell them, even in this example, it's not detention compression in members. Compression members basically get to yielding, buckling. Now we may not cover buckling solid mechanics, we may or may not, but if we tell them right away and then show a demonstration using like a scale, long scale or a long bar in the classroom, they will then appreciate that. So before it gets compressed, it may buckle, and then leave it at that point for the equations to be discussed maybe later if you cannot cover it. But discuss the different modes of failure in a truss. For example, the pins may fail, the members may fail, the support itself may fail. So just engage them into discussions, although you may not use the equations for it. The emphasis here is to compute a load and its stress. But still we need to discuss different other failure modes. Go to the next slide. So now we're taking to a slightly different level the same examples. Bridge that fails. A bridge is not really a truss. Truss is an assumption. Maybe this is a frame or a grid, because the bridge members, they are riveted, so there's no pin joint. So there's nothing like an ideal pin joint. So now we are showing reality. And now showing this picture is a bridge which is failed, maybe in USA or England or maybe in India. But if they've seen it, you can ask them to explore, bring it to the classroom, failed bridge, and maybe from India, maybe from Singapore, maybe from USA, any bridges, and then ask them to discuss the safety and impact on society. So that's the thing I emphasized in every example. So you give them homework, ask them to find a practical application of that homework with those numbers, with the data. I'm sure they cannot find it quickly, but let them struggle a little bit. And some students really bring those examples. And then, once they find the real life application, discuss the safety and consequences society. For example, what is safety and the impact on society? In this example, the safety is the one that if I am the unfortunate person trying to cross the bridge, if the bridge collapses, then myself, a car, we get down. So it's not only the safety to the passengers currently on the bridge, Could be train, it could be bus, could be walking, it doesn't matter. So the safety is not just limited to persons who are on the bridge. It's very important, of course, but we need to design bridges as they're getting older in all countries, the whole world. That's one issue we can discuss. Why they get, when they become old, why should they fail? Because of accidents, whatever, because rust, that's a different discussion, but we can engage them that will basically question the assumptions that we are making, like ideal joints. And the safety is not only to the persons traveling on the bridge at the current time, but the societal impact. Because once the bridge collapses, there's no connection between the other two sides. Maybe there could be two islands. There could be, so now people have to go around. There may be perishable goods waiting to cross to the other side. They can't cross. So it's going to impact the society. It's inconvenience as a whole, right, to the society. The society is not just confined to local people, but people come from maybe different other states to cross this bridge, like a Krishna barrage or Godavari or any Brahmaputra. All these bridges, if they collapse, obviously there's going to be disruption of traffic, and that's going to cause impact on the society. The cost will increase. The goods have never delivered on time, delay in constructions, delay in supply of medical equipment, if they have medical supplies, medicines, perishable goods, and so on, right? So you can just engage them, the societal impact. So now coming from a homework, find an application, and then the safety of that application. The homework might be confined to a two-member trust. That's okay. But the two-member trust is part of a big bridge. And now we discuss ideal joints. The students will see and we get mature thinking in questioning the assumptions, and then the safety and societal impact. So that's going to be tough. Not all examples have this component. So basically start with concepts, find an application, and then take them further. So then you're taking the Bloom's taxonomy higher up and up. The tension loaded joints, if they have seen a hitch in a truck, basically then this hitch which is attached to a trailer and the truck or a car. This is perhaps not commonly seen in India, but other countries is very common. I'm sure India also has seen truck trailers, car trailers on a hitch. Now, when we discuss the tension loaded members, the left-hand portion on the hitch right here. So this one is subject to tension. It's actually combined loading. We are pulling it here. This can break. That brings us to the modes of failure. It can break here. This can get pulled off because it's welded. There are different ways it can fail. We got a pin. But if you look at only this section, draw a free body, basically that's in tension. So we can ask the students to explore this application. They may not have seen it. They might not have seen it, but they should explore on the internet to find the cross section of this. Now, and then of course that becomes a real life example from a simple tension example. And also now they can discuss the safety, societal impact. Now, if this fails on a high-speed interstate, it will go at 80 kilometers per hour or higher in other countries. You can't afford to get the trailer detached because this failed or this failed. So when it gets detached, then it's going to be dangerous, safety issue. And also again, if there's an accident, the road is closed, it becomes societal impact in some way. So it could be 2 hours, it could be 10 hours delay because of disruption. So we know those accidents in India, in other countries, we see those. So discussing these two and how you design components will bring us to the 5 E's. We engage students, they explore different other designs, opportunities, they're able to explain, they're not in any sequence, but basically they evaluate the design, they can elaborate, communication, and then explain those. So these 5 E's become very important. So go to the next slide. So we need to bring this in every level. So they can easily find the dimensions for a tension-loaded kind of a hitch, and where it's connected on the truck, and what the assembly looks like. So there are many websites. We can't show them every day in the class. If you don't have computer connection, at least you can show them these figures and then ask them to Google search or use these links to explore further. And I'm sure they will do it. Okay, go to the next slide. So that's a photograph basically from my own vehicle, but not all of us have this system. But now we're talking about, I asked them to explain the difference between this and the previous slides, then they should be able to tell there are chain links. What's the purpose of that? You know, if they break, then of course the chain links are engaged. In this case, that's a secondary backup safety system. So then the chain links are, once this breaks, it takes some time for the trailer to get detached, because now they're chains. It takes some more time for the chains to break. Chains will break because it depends. Now the trailer speed has reduced, likely because the truck is also reduced, truck or the car. You may not have noticed it. You're going still at full speed, but this one got detached. Then there's a sudden thud or a pull on your car, and then the chains are engaged. The chains will also break quickly, but it won't cause too much disastrous accident if there are no chains. So it's a gradual detachment, and hopefully the drivers behind react to the oncoming accident, and they may control the speed. So all these discussions will help. We are not really engaging the students to design the links if that's necessary. By the way, there are federal regulations for us in all the countries. The federal regulations. You can also use ropes of some kind. So there are different chain links, chain designs that the students can explore. And then the regulations means there are standards. So you're really teaching all of them in one go, in small classroom discussion and in a homework. So that will probably engage them to these 5 E's. Go to the next slide. So the 5 E's are inbuilt in the Bloom's taxonomy pyramid, and I gave a web link here. If we have time, we will open it. But this web link that contains some examples for your different classes. This one is developed by one of the colleges in New Jersey, United States. I did receive a mini grant to develop some examples to contribute to this bank of different examples. So I'll show you an example in the next few slides. Go to the next slide. So in active learning, Piaget, he said, education which is an active discovery of reality is superior to one that consists merely in providing youth with ready-made truths. So if you tell everything to them, I know students don't like, they want to be told, but we engage them in discussion and then to reality, and then don't judge. If they do mistakes, that's okay, but get them to talk in a classroom. Again, don't think that it's going to consume all the 50 minutes of your time. Usually, you know, the attention span is only 10 to 15 minutes maximum. Nowadays, they say it's only 5 minutes. So after 5 minutes, we should stop the lecturing, and not many of us do it, just like myself now in this webinar. Basically, we should, after 5 minutes, we change the activity, showing a YouTube calculations, some of those things. We all do it in a variety in a 50 minutes, so that all the 50 minutes are completely used. For us at catering, we have 2 hours block for a classroom. So 2 hours is quite a bit. So basically, we cover a lot of concepts, applications, and then they start working on some classwork. And I also help them with tips on the homework. Think ahead right in the classroom in front of me how to solve the homework problems. But I don't solve them. They don't solve it. They understand the process to solve the homework. So that way they get more motivated. And they take 5, 6 classes, and they don't have time in a week. So that will really help them motivate and reduce cheating. Cheating, just not copying. They understand how to solve a problem. So there are some of the things that we do in active learning, and that's again a big field by itself. Okay, go to the next slide. Now these are some of the examples from FEA, fundamental analysis. Now it's a little bit, this is just a CAD geometry. We build what's called impact tester for testing dummies. We have a crash safety lab that required a design of this. So student expressed an interest to design this for FEA class. I immediately let them do it, and he actually built it based on these several designs. There should be standard sections that are available in the market, and everything should be standard section, and also optimize the length and the different sections so that the stresses stay within limits, and also deflection stays within limits. So it's a small project for the student. And then obviously it's at a very higher level in the Bloom's taxonomy. A lot of analysis. They'll do crude calculations, how to reduce model because of symmetry. Can I reduce this to simplified mechanics problem? Yes, I can see a frame here. I can see another frame on that side. So how to reduce this complex system into a simple model? This itself is a model, but how to further simplify it in using symmetry is part of FEA. So I asked them to do quick calculations, hand calculations, based on mechanics. So how to reduce all this into a single member, equivalent member. It won't be exactly correct, but that makes them think. So that thinking is very important. I can go to the next slide. When we teach the grid analysis in FEA, the grids are one is a frame, one is a grid. Grid is the one in which apply the load perpendicular to the plane of the frame, and then becomes a grid. The grid has both bending and torsion. So that's the difference between a planar frame and a grid. Obviously, in real life, everything is like a grid. Everything has a twisting and also bending. It's not just bending only. It's a combined loading. So this student actually happens to do climbing, rock climbing or climbing on a rope. So he also designed for himself for a rec center. So question is how to join two I-beams. This is computer generated drawing. But to actually make this, I can make this I-beam, can make this I-beam, but joining those two, that's not easy. You know, you can weld it, you can put gusset plates. So those are the ones that discuss in a basically maybe a lower level graphics class or a CA class. But FEA class assumes it's joined somehow. And but this student also did three-dimensional modeling of the same system with some kind of welding, or could put rivets, bolts, etc. Okay. So you can carry on further to make it complex and close to real systems. Okay, go to the next slide. We have at catering a running track. Yeah, this becomes like a real life example. We got a running track, so students can run. So there are a lot of frames, structural members in it. So these members are subject to axial loading, for example. This whole floor on which students run, it looks like a cantilever beam. So they need to make modeling that looks like a textbook problem, and that's not easy. Then again, the assembly, how they join, and then of course the safety and societal impact issues. So if the rec center is this recreation center, safety is the one for because the load carrying capacity is limited to so many members at a time running on the track, and that's related to vibrations, resonance. How many members can collapse at what frequency becomes a higher level problem. It's not easy to solve it, but at least they can solve it in a rough way, vibration problem that requires a lot of data. And they can explore it. In this case, the student explored the data by using a tape measure and some eyeball judgment. So that's when they can understand the perspective, vision, how to scale it and estimate how much this might be long. And he used the standard, because there should be a standard dimension. It can't be 24.8, so it should be probably 25 feet, close to 25 feet. So tension loaded members, we got beams that bend, the whole floor members. So it's very complex. It can do a lot of stuff on this, but it's a real life example. He measured the cross-section dimensions and then found the load carrying capacity, etc., of a real life. Now, what is this to do with societal impact? Well, in a university, if there's an accident, if this collapses, that becomes concern for many parents. So they may or may not send their kids to this school, because then they say, well, the school is not safely designed, recreation center, all the labs, buildings, nobody will send them to the school if it is poorly designed structures by the engineers, by the contractors. So now the enrollment goes down, the reputation of the school goes down. So that's a societal impact that I can think. So I can engage the students. A single accident can cause a lot of other repercussions. So that thinking itself is good enough. Okay, go to the next slide. Now, bicycle frames, this is SAE formula car. The students are there, probably some universities have it. Go to the next slide. When we discuss axis symmetry, paradigm analysis, then of course there's a difference between axis symmetry and cyclic symmetry. So this is not exactly axis symmetric because there are holes. So maybe it's a cyclic symmetry, but at least for a first cut modeling, they can do axis symmetric modeling in FEA, if you understand what that means. And then basically this is for estimating the stresses when it's assembled, maybe centrifugal forces on a wheel, and then they can do a cyclic symmetry and then do a full model in FEA and compare the results. So now you're doing comparison, so that brings them to a higher level. Now it looks like huge projects, but nowadays the students have a lot of skills with CAD geometry, and particularly if you give this as a group project, a group of 4 or 3, then we're trying to engage each student in the project so they can develop different models. I think we do all these things in classrooms. This is nothing new, but I'm just trying to emphasize if we can bring it to a lower level class, some of these real life examples. Okay, go to the next slide. Bench press for distributed loading. Okay, so now I understand the point, the supports, the weight that you put here. So you don't give nothing. We don't give any data. This one is not it's uniformly distributed, but there's also difference in if you put smaller weights, then of course intensity is going to be different towards end. So let the students figure out. That's the problem, textbook problem. They know how to solve it. They are now relating that to an everyday example, and then also discuss that with the classroom, and then see how they modify this problem to a different scenario. For example, if there's a heavyweight champion, weightlifting champion, they need to use more weights, so this intensity is changed. If the same thing is used for a kid, like 10-year-old, with the proper supervision, how do you modify equipment to a smaller kindergartners, in a high school, or even below that? How about girls using it, boys using it, small kids? So how do they modify the design? So that brings to a different level in the Bloom's taxonomy. If you just solve this problem, that's the lowest level application, find another application. So that basically interests them. And then ask them to study different other designs from internet search, and then report to the class. And that'll be a good small projects, mini projects. Don't postpone it for machine design or capstone. We should try to do it at undergraduate level, at the solid mechanics, for example, or FEA. Again, discuss safety, societal impacts, etc. Go to the next slide. We have common millions of these stop signs. It's a very common example. It looks like unimportant, but it's very important. When you have winds, gusty winds, then it's going to oscillate. They can study vibrations of this. They can do solid mechanics, societal impact, because there are millions of these stop signs. How high it should be. It should be a certain distance. There are standards for it. It can't be too high, too low. It should be visible to those who are driving. And the color scheme, the letter size, they're all standard regulations for it. So how do you know the student actually went? So I take one step. It's not copied from internet. So basically I asked the student to take a picture of themselves and include in the report. And so basically then I know that the student gone to a certain real post. The student, so if you look at the cross section, it's very interesting. I'm not sure if they have stop signs of this kind in India, but they can explore it. Just one outside their campus, or they're going to a city, and if there's nothing, then they can explore from internet, from other resources. So it's very hacked section, and discuss why it has to be hacked like this. Why not I-beam? Why not rectangle? Why not box section? Why not round? And then there are holes in it. Why should there be holes in it? To escape the wind. So this will bend, also twist. Torsion of this is very tough. We don't teach that, but in regular solid mechanics class, and we may teach it, but it's very tough. Teaching torsion. Bending is okay, then you need to find the moment of inertia. It's becoming challenging, right? So it's the application of moment of inertia to real life, and then of course they can come up with maybe different designs of this. So so there's a lot in it. There's standards, safety standards, regulations, design, and then the production of these. There are millions of these stop signs in different countries. So it's not just this one. There are different road signs. I know India has many interstates, highways. There are many road signs now. So they're not maybe millions, but it's going to get there. There will be many hundreds and thousands in India also, because they're building many highways. So we are not civil engineers, but we are mechanical engineers. But still, that's a structural engineering that we can use for the classroom. Okay, the next slide. These are called everyday examples, but for us it's every day, but in India it may not be. So the consequence of poor design, societal impact, we already discussed that. We can go to the next slide. So recall is a bad thing. So that's a societal impact, because they're going to increase the price when there's a recall. So recalls are very dangerous. It shows the poor image for a company. So most companies have recalls. unfortunately. But that's a consequence. So it's just a discussion of it. We can't solve this problem, uh, but it's just a discussion and the impact. Okay, go to the next slide. I'll show a couple of other documents. Student comments, basically, you can see this. The general feedback was okay, but some group members felt it's a lot of work because either they did not like it, real life examples, or they start in the last minute, or they have too much workload. And I tell them, if you have too much workload, let me know. Then I give you another alternative homework assignment. But my homework has to have some application. If you give 5 problems, they may or may not be able to give us applications of all the 5 homework problems, but at least one of them. They attempt to bring us one application that they understand. Now, open-endedness, students hate ill-defined, not well-defined, ill-defined problems. If it is open-ended, they will never like it. But in the entrepreneurship, innovative teaching methods, and the Bloom's taxonomy, we can't define everything, and that's the lowest level. So we need to tell the students, this is why I'm going to teach you. Maybe show the Bloom's pyramid and tell them the purpose, that they have to think like engineers. In real life, nobody tells them well-defined problems. If there's well-defined, we don't need bachelors of engineering. Any high school student can tackle those. So usually they're ill-defined. So we're asking them to appreciate that. So some students obviously think that, well, I'm paying my tuition, so you better teach simple things and textbook, and don't give us many projects. So, but that's minority. And but this one they liked quite a bit: societal impact and pool design. Okay, go to the next slide. Okay, so basically the ambiguity in the data collection is very important. Data collection, I don't give data. They need to go and find the data. How much wind is coming on that stop sign? So then they need to do internet search, research in that area. What is the wind speed? The gales, if there are severe winds, they have to figure it out, the data. And then that has to be translated into how much load is coming on that stop sign, a physical load. So they need to understand the area, wind velocity, all that stuff is fluid mechanics. Now you're connecting 2 different classes, fluid mechanics with the solid mechanics. Again, we do those, some of us do those, and you can challenge them, let them do mistakes, but let them find out the correct formula to estimate the load, wind load, into a structural load on the stop sign, basically. So there are many kinds of stop signs. Recreational equipment, road signs, buildings, they are very good examples in solid mechanics. Okay. Go to the next slide. I'm sure now I want to show you one more document before we conclude and take up any questions. I will be, this time, every winter time is my off term at Kettering. Normally I travel to foreign countries. Last time I went to New Zealand for 4.5 months. I taught non-linear FEA. We used ANSYS in New Zealand. And I would love to, this time I'm going to VIT. They invited me, Vellore Institute of Technology, Vellore University. But I will be available in India if any of you wanted to spend some more time, maybe a week, 2 days, 3 days at your place. I'll be more than glad to come and discuss and implement 1 or 2 examples, action items, not just talk, but we can do together something if you're interested. Okay, so I'll show another document if we can. There are some more slides, but you can look at those. But I will stop this presentation, but I'll show another document. If you can get out of this, you can close this. And let me see if I can. So how do I load? Okay, I can close that and then show me screen. I'll show another bookshelf. So here is an example of a bookshelf. I don't know if you can see it.
No. Did you press show my screen? Yes, now I can.
No, I can see it. Okay. Can you take over to show this?
No, it's on your computer.
I have to do it? Okay. So this is an interesting example. When we discuss distributed, you can see this, right?
Yes.
Okay. This is from a textbook, basically. Simple example. Load on a beam, distributed load. Now, what's a real life can be? So I showed them bookshelf, for example. There are different kinds of bookshelves. So each group took different bookshelves. The way it is supported, that's a side view of this bookshelf. They did the measurements of the bookshelf, how much each book is going to weigh. I didn't tell them, so they got to put the books, the different size of books, each one of them weigh different. So now we got variable distributed load on this. The goal of a bookshelf is to reduce the deflection, not so much on the stress, but just the deflection, so the books won't sag. So they came up with different designs of this member, supporting member, and this bracket, and the cross section of the bookshelf itself, panel. So they analyzed the cross section of this, and they varied the length of this, standard length in library bookshelves. They came with, you can see this clearly, rectangular cross section, do the calculations, a T section for the beam, channels, and other sections possible. They should be manufacturable and not just drawing. So they discussed all that in a report like this. And they submitted this for safety concerns because the books fall down. If you're sitting underneath the bookshelf in a library, if it falls down full of books, then it's going to be a bad show. Of course, there's also concern for breaking or causing some accident to the body. And then they explore and come with different other designs people use to reduce the deflections. So here is a seat as a part of the shelf in some book design. And how do they equalize? So somebody can sit down on this and then read, put the book back. Now, in some buildings, it's possible to have bookshelf below the staircase. So that's an innovative idea for a bookshelf. So, the students actually brought these ideas. So they collect ideas from different textbooks. Okay, that's one example. So let's quit this and then go to, so how to do that? Let's see. Okay. I just want to show one last. Can you see this now? Can you see this? Hello? 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 Okay. Are we done? Are we done with the webinar? Hello? Hello?
Yes, sorry, my power is gone.
Oh, power was gone, that's why. Okay. But we are done, right?
Right, yes.
Okay.
And
Um,
so some of the participants are saying thank you to you for the presentation, and
no,
some
thank
have
you.
requested it. I'll send it to them.
Okay, please. Yeah, you can feel free to send the PowerPoint. I'm sorry, actually. I'll also send you the bookshelf example. They want to use it.
Sure.
And they should particularly go to their website. Um, I'm not sure if you can see, because we're out of the presentation mode, right?
Right.
So, okay. On slide number, let me see, that's a slide number 41.
Okay.
There's a website. It's called www.engageengineering.org.
Okay.
Usually they don't respond if somebody writes to them from other countries, because this is limited to, I'm sure they would like to, but I haven't heard from them. I have a mini grant from them to develop real life examples, and
Uh-huh.
but some of the material is available. You can try, that on slide 41.
Okay.
They can manage, and they can go there. Some courses, dynamics, statics, mechanics materials, I think fluid mechanics. It's just a contribution from different instructors, such as myself. What I do in the class, I share that with the college. It's in New Jersey.
Okay.
So basically, they collect all the sources from professors and their feedback to share to the public, to the other professors. So they should go there. I don't know how to. You can send that contact, slide 41,
Yes,
and
I'll
then
put it up separately on the website.
yeah, separate email to them, and then
Yeah.
somebody already wrote to me from Aurangabad, email, and if anyone of them interested to take it further, so maybe in a matter of one day, if I go there, or 2 days, we can have the students come up with different examples, and all of a sudden we'll have 10 to 15 different examples, that student-generated examples. I can use the template that I'm going to send you.
Okay.
They use that template or any other template to generate a report, and that will be useful for the professors. Okay. So I really enjoyed, and thanks for giving me that opportunity. I hope it went well.
Yes, sir.
And anything else that we need to cover?
Yeah, I will post these and also let you know the link where I post them.
Yeah. And then any of them want to explore further, I'll be more than glad, because the last slide tells I'll be in India. And so I'm in New Jersey right now. I'm away from home. That's why there's some. I'm not completely 100% happy with what I showed, but there's also other lectures, like I told you, the other lectures like in aluminum, design with aluminum. If you're interested, we can organize on a different day. I'll be at home then, my own home.
Okay.
And that works better because it's not my computer here. So, okay?
Sure. I'll send you the date, possible dates. Yes.
Yeah.
Thank you very much, sir.
All right, bye.